still the early morning. Maybe some of them are still trapped in traffic, but they could watch the talk by their phone. Okay, so today is our great pleasure to have Suzette Timmerman speaking us from University of Minnesota. So Dr. Timmerman spent her early days in Netherlands and then went to Australian National University for a PhD before she became a postdoc, currently at the University of Alberta. So today she's going to talk about the work, the publication, the work that relevant to a publication that was published in Science in 2019. So with that, I will give the rest time to you. And this is a semi-formal seminar, so it's more like chatting with your friends about science. So we are quite casual in this style. So you could go along for 40, 45 minutes according to your own pace, and later on the audience will interact with you. Okay?
Sure. Well, thank you very much. Today I'll be talking about some of the work I did during my PhD. And yeah, I got a range of samples that I studied during my PhD, lithospheric diamonds and sublithospheric diamonds. And I saved the sublithospheric diamonds right till the end, because a lot of them have like, yeah, we didn't know how many fluid inclusions would be in there, so how many Nobel gases we would find. So I first focused on the other samples to really get familiar with all the techniques before doing the precious super deep diamonds. And I got some funding from the International Association of Geochemistry to actually visit the University of Alberta to do the trace elements and isotopic work. And I did the Nobel gas work at the Australian National University. So why are Nobel gases important? So Nobel gases don't have any bonds with other elements. They're very volatile, they're incompatible, and they have a very high diffusivity. And this makes them very sensitive tracers to look for homogeneity in the mantle, to look for melt migration, mixing between different fluids, fluid-rock interaction, the evolution of the chemistry through time, and also the origin of related volatiles such as water and CO2. So just first a short introduction to Nobel gases. The 5 main Nobel gases are helium, neon, argon, krypton, and xenon. And for helium, we've got 2 types, free helium and 4 helium. Free helium can be formed both nucleogenic, by nucleogenic reactions and by cosmogenic reactions. And obviously the free helium that was already present on Earth, we call primordial free helium. 4 helium can be produced by uranium, thorium, and samarium radiogenic decay. And then for neon, we've got 3 isotopes, of which 21 and 22 neon can be formed by nucleogenic reactions again. And then I won't be focusing on any of the other Nobel gases today. So just a short introduction. As you can see in the graph on the left here, we've got the range for MORB, which is quite limited compared to ocean island basalts. And from now on, I'll be using R over RA, which is the free helium over 4 helium ratio of the sample divided by the free helium over 4 helium ratio of air. And air is defined as 1.4 times 10 to the minus 6. And as you can see, the ocean island basalts have higher R over RA values compared to MORB, except for a lower frequency of ocean island basalts that actually have very low R over RA ratios. And as we can see on a neon versus argon isotope plot, again, the neon isotope ratio is relatively higher compared to the argon ratio for ocean island basalts relative to mid-ocean rich basalts. So helium isotope compositions with basalts play a critical role in defining models of Earth's chemical structure. And the high 3 helium, 4 helium ratios of plume related basalts relative to mid-ocean rich basalts are taken as key evidence of a primordial undergas reservoir with high 3 helium, 4 helium ratios present in the Earth's lower mantle. However, the preservation of such a reservoir over the Earth's history has been questioned based on geophysical evidence of slab subduction into the lower mantle. Further, helium isotopes in vessels are affected by plume entrainment, degassing, and crustal contamination. An upper mantle location or formation for the high free helium-4 helium reservoir has also been suggested based on seismic tomography anomalies in the upper mantle and low uranium thorium over free helium domains formed through melt depletion during oceanic and continental crust formation, and also heterogeneities in the upper mantle sampled by small degrees of melts. So within the mantle, we've got a couple of important but poorly characterized reservoirs for nova gases. This is subducted material, the subcontinental lithospheric mantle, and also the deep mantle. So the subcontinental lithospheric mantle and the deep mantle have been highlighted in yellow boxes on the figure. So the continental lithospheric mantle is a significant terrestrial reservoir, which actually represents approximately 2.5% by volume of the total terrestrial mantle. And the deep mantle is, of course, an even larger reservoir. So the nova gases, the extent, the timing of the gassing, but also the inputs of nova gases back into the mantle and the source of the volatiles are not well established. And we need to know these things to develop a better high resolution model of the Earth structure. And for the nova gases, in particularly helium, we know the present day helium isotope value of the upper mantle reasonably well through mid-ocean ridge basalts. And we know what we started with based on meteorites and other models. But what happens in between, we don't know very well. How the helium isotopes have evolved through time in the mantle. So this is where diamonds come in. So diamonds are inert, so we don't have nova gases basically moving out or moving in. And diamonds have a large age range of about 3.5 billion years ago up till present. And they grow from supercritical carbon, hydrogen, oxygen, and sulfur-rich fluids. These are all volatile-rich fluids, so they also contain a relatively high abundance of nova gases. And the majority of the diamonds form in the subcontinental lithospheric mantle, which was mostly formed in the Archean through melt depletion, and this made them extremely buoyant due to loss of iron, but also because of the loss of uranium, thorium, and potassium, which are heat-producing elements. The subcontinental lithospheric mantle is relatively cold, which raises the graphite diamond's boundary and leads to diamond being stable in those parts of the lithosphere. The other part where diamonds can form is associated with subducting slabs, where conditions are oxidizing enough that we can actually form diamonds all the way down into the transition zone and possibly the upper parts of the lower mantle. So fibrous diamonds that we mainly see in the lithospheric mantle contain lots of submicron inclusions, and this makes them very cloudy, whereas monocrystalline diamonds only have very sparse fluid inclusions that are usually found at the corner of twin planes. So in order to liberate both the trace elements and the nova gases, we use different techniques. The trace elements in the fluid inclusions, we can get by ablating a lot of diamonds, and then we hit several fluid inclusions, and we actually dry the ablated material down in HCl, and then we can take it up and measure it by solution modes by ICP-MS. In the nova gases, we can either release the nova gases by crushing from the diamond. So as you can see in the images below, when we crush the diamonds, we actually expose the fluid inclusions, and this will release the nova gases into the mass spectrometer. We can also do it by heating. We then graphitize the diamonds at about 2000 degrees Celsius, and this will, when the diamond turns into graphite, also releases the nova gases from the fluid inclusions. So there are different upper mantle models because we don't really know that well what goes on with the helium isotope composition in the mantle between the beginning of the Earth and present day. And there are several people who have looked at no big gases in diamonds before, but we only know the minimum age constraints based on the eruption age of the kimberlites that rolled up the diamonds. In addition to that, we don't know their uranium and thorium and samarium content, so we can't correct for the 4 helium ingrowth. Further, the diamonds can be affected by subduction fluids, and within the subduction that brings in a lot of extra uranium. So as you can see on the graph on the right, some of the diamonds that I actually studied, we can see for the eclogitic diamonds, some of them actually have relatively higher uranium contents compared to free helium, relative to the mid-oceanic rich basalts and the depleted mantle. So this actually means that the subcontinental lithospheric mantle is getting extra uranium in from, likely from subducting slabs. And Hart et al. 2008 actually modeled what would happen to any helium that would be created by decay from uranium in the subducting slab, and what effect that would have on the helium isotope composition in the surrounding mantle. And as you can see, that with time, obviously part of that helium diffuses out, and it lowers as well through radiogenic decay, so we're forming more 4 helium. But you can also see that in the lower graph, if you have a thicker subducting slab, that profile will be a lot steeper in the beginning. So you're actually preserving more of this low R/RA composition in the subducting slab. So we can see a signature from the helium in the mantle from subduction fluids. So even though helium itself is likely not subducted, because we subduct relatively a lot of uranium compared to free helium, we can still create really low R/RA ratios. So I looked at diamonds of which we've actually dated them. I did my master's and also during my PhD. And of these diamonds that we know the ages from, I also did the ablations to get the uranium, thorium, and samarium contents, so we could correct the no big gas data for the radiogenic decay. And as you can see, some of them still actually have quite low R/RA ratios, and this is because of this subduction influence that I just mentioned. But when we use sort of the upper values that we have found so far, we could sort of indicate what a potential helium evolution could look like in the subcontinental lithospheric mantle. And we know from the most recent ratios that they're actually lower than the upper mantle, but it looks like this is a more recent thing, where basically since subduction began, the helium evolution of the subcontinental lithospheric mantle has been going down quicker compared to the upper mantle in terms of R/RA ratios. So now onto the primordial reservoir. So in the lithospheric samples that I studied, I didn't see any high free helium, 4 helium ratios. And as I discussed before, a primordial reservoir could potentially be present in the lower mantle or in the upper mantle. But we don't really know much about what is happening in the transition zone and lower mantle. So that's why we looked at the diamonds from those depths. So for the super deep diamond samples, they could provide a new view on the helium isotope composition of the deep mantle. And as you can see in the image below, some of those super deep diamonds actually contain clouds with a lot of fluid inclusions. So hopefully, we figured they would have a lot of helium to measure. So we focused on 3 locations, all from Brazil. So we've got the Juína 5 kimberlites, the Collier 4 kimberlites, and alluvial diamonds from the São Luís River area. And all these locations here are known for their predominance of super deep diamonds, with over 99, if not 99.9% of the diamonds coming from the transition zone and the lower mantle. So how do we know that they're super deep diamonds? So first of all, we can look at mineral inclusions, such as jasponites, calcium perovskites, majorites, and ferropericlase. And these mineral inclusions and combinations of those will help to provide depth constraints. In the case that we don't find mineral inclusions, we can look at, for example, the growth structure of the diamonds. The super deep diamonds always have a very complex growth structure or very diffuse growth zones. And further, the super deep diamonds that people have studied so far, they either have fully aggregated nitrogen or no nitrogen in the diamonds. So what happens is when there is nitrogen in the diamonds, first one nitrogen atom replaces one carbon atom. And with time, the nitrogen atoms basically look for each other and they become pairs of nitrogen and subsequently 4 nitrogen around the vacancy. And with FTIR, we can actually see the different peaks of these different types of nitrogen. And the aggregation of nitrogen is dependent on the concentration of nitrogen in the diamonds, but also it's dependent on the temperature at which this happens and also the time, but mostly the temperature. So our samples show indeed complex or diffuse growth zones. As you can see in the right, a lot of these growth structures in this cathodoluminescence imaging, they don't show very sharp growth boundaries, they're very diffuse. And all of the diamonds had a type 2, so no nitrogen, or fully aggregated nitrogen from FTIR, as you can see in the graph below here, where we see no single or 2 nitrogen, we only see 4 nitrogen around the vacancy. And some of the diamonds did have mineral inclusions, such as this one over here. On the bottom right, we can see a Raman spectrum, which shows coiosides and calcium silica wallstromites, where the calcium silica wallstromites is likely to be a former calcium perovskite. So subsequently, after the sample characterization, we analyzed the carbon isotopes by shrimp. We ablated the diamonds to get the trace elements, and then re-ablated some of these diamonds for lead and strontium isotopes. And subsequently, the remainder of these diamonds from the same growth zones, we selected fragments to do helium isotopes. So we're really measuring down to the very limit of what we are capable to do today. So we measured a lot of standards, for example, for the leads and the strontium isotopes, to measure down at sort of the same level that we were expecting. And as you can see, even the smaller standards are very reproducible. And we had some of the lowest leads digestion and column blanks ever obtained. So we had some that were, down to about 0.17 picogram of lead. And we had very consistent isotopic compositions for the blanks as well, which is really important when you have to make a correction. So as you can see over here, for example, for the lead isotopes, the average blank composition over here was falling to the left and actually only had slightly larger error bars than most of the samples. And as all of the samples actually plot to the right on the 2x6, 2x4 leads compared to the blank composition, the blank correction will only push these values further to the right when we subtract the blank. So when we look at the corrected values on the 2s7, 2s4, 2s6, 2s4 lead diagram, you can see after the blank correction, they would have moved further to the right, and you can see they're all plotting within the Morb fields, and 2 of them are actually similar to high mu values. And they're very different to the circles that you can see over here, which is from lithospheric diamonds. So for carbon isotope compositions, the carbon isotope composition is expressed as the 13 carbon over 12 carbon ratio of the sample relative to standards. And we look at what happens in the third decimal. So it's expressed in per mil values, the deviation. And as you can see, the mantle value is around -5 per mil. And a lot of the periodic mantle samples show this as well. Whereas eclogitic samples that show recycling inputs actually have values down to about -40 per mil. And people have also looked at oxygen isotopes, where we can actually see higher oxygen isotope values are for a more recycled input, whereas the mantle value is around +5 per mil. So as you can see in the top left diagram, these are the range per sample. So we've got in green, we've got the Collier 4 diamonds that we studied, and we had 5 diamonds. So each row is basically representing the range within a sample. And as you can see, a lot of these samples had a reasonably small range within the diamonds. But you can see we actually have, between diamonds, we range from about -3 all the way down to -27 per mil. So we really get that subduction input, particularly in the Juina 5 samples. So from Juina, other people have studied samples as well. So Burnham et al. Looked at the oxygen isotopes of the mineral inclusions. And as you can see, relative to the carbon isotope values of the diamond hosts, some of these samples go to lower carbon isotope values and higher oxygen values. So we really see that recycling inputs. Some people have looked at ferropericlase for the lithium isotopes. And again, you can see that these super deep mineral inclusions show isotopic values that are typical of recycled material. The same for our strontium values. In the diamonds that we studied, a lot of them are very radiogenic, and this is unsupported by their present day rubidium strontium ratios. So again, we must have relatively old sediments or crust that subducted down there that had high 87 strontium, 86 strontium ratios. So from multiple lines of evidence, we actually see that there is a recycled material input in the transition zone. So these are some of the trace elements that we measured for the studied samples. So the extremely low trace element concentrations of these sublithospheric diamonds are caused by the sparsity of the fluid inclusions. So they're not a direct measurement of how enriched or depleted the growth environment is. However, the trace element ratios can provide information on the sources and the processes. So the large light rare earth over heavy rare earth fractionations that are found in some of our diamonds, which you can see in the figures here, are consistent with derivation of low degree partial melts. And the yttrium holmium anomalies that you can see in the bottom left figure over here for 2 samples, they have been related to subduction before, whereas seafloor ferromanganese nodules actually show these similar weird iron yttrium holmium anomalies. The signature could also be related to partial melting of some of the high pressure minerals, such as sodium aluminophase, calcium ferrite, or bridgemanite, that also show these anomalies. They could also even be present as micro inclusions in the diamonds. So sometimes we don't only find fluid inclusions, but also micro mineral inclusions. However, the original formation of these minerals likely involved subducted material as well. The negative europium anomalies could be related to old crustal pelagic sediments, and strontium anomalies have been related to fractionation of feldspar at shallow conditions, both of which are again suggesting that subducted material was involved in the source of these fluids. Finally, the negative zircon hafnium anomalies could be related to garnet and zirconium oxides, particularly as zirconium is being preferentially retained over hafnium. So a little bit more about the helium isotope composition. There are certain ways in which we can modify the helium isotope composition, which is through helium diffusion, the creation of radiogenic 4 helium, and nucleogenic and cosmogenic 3 helium. So first on helium diffusion. So the experiments that have been done show that before helium diffusion is extremely low. And on the right, I plotted for different diffusion rates. So the top two ones in blue and red are the ones that was the range determined by Shelkoff et al. In 1998. And as you can see, even after 1 billion years, we only have a few tenths of microns of movement of 4 helium atoms in the diamond lattice. However, because the Nobel gases are in fluid inclusions, it's a lot harder to jump from a fluid inclusion into the diamond lattice. And it has been estimated that the diffusion from a fluid into the diamond is actually about 4 orders of magnitude lower. So then you can see that after 1 billion years, we only have about 1 micron of movement of the 4 helium atoms. On the left, you can actually see where we've done different parts of diamonds to measure for Nobel gases. This is some work I also did during my PhD. And this is just one example. We had several diamonds where we could actually see a significant difference in both the concentration of 4 helium and 3 helium and in the isotopic composition between different growth zones. Again, suggesting that diffusion isn't significant because otherwise differences in isotopic compositions would have been removed. So radiogenic 4 helium is formed through the decay of uranium, thorium, and samarium. And that has a certain energy when that happens, and it can actually eject the alpha particles. So an alpha particle is basically 4 helium atom, but without its electron still. Same for if there's material like the kimberlite surrounding the diamonds at the Earth's surface. And the kimberlite contains a lot of uranium and thorium, and that could actually implant helium into the diamond. But this only affects the outer 30 microns. And as you can see in the diagram on the lower left, Shelkoff et al. Actually tested how the 4 helium concentration changes when you go into the diamonds. So what we've actually done is that we have removed the outer rim for all of our diamonds prior to the helium measurements. So we avoid the whole issue on 4 helium implantation and also 4 helium ejection. Finally, we have corrected our samples with an arbitrary measure of 500 million years. So based on previous studies of mineral inclusions in the diamonds in the Jurina area, it suggests that all of the diamonds are likely less than 500 million years old. So this is sort of an upper limit about how much 4 helium could have grown in since diamond formation till present. And we see that for the majority of our diamonds, this makes a difference of less than 0.8 in the helium isotopic composition, which is not much compared to the range of compositions that we see. And finally, for the 3 helium, this can be created by nucleogenic reactions. The main one is by 6 lithium. And we've calculated based on estimations of the lithium concentration in diamonds, and again, sort of an upper limit for the age of the diamonds, that less than 0.3% of the helium is from nucleogenic sources. For the cosmogenic 3 helium, this is more difficult to calculate. There are still further studies needed to quantify this better. But we do know that because of the cosmic rays entering the Earth's surface, it only mainly affects the upper 1 meter. And there's an exponential decrease as soon as these cosmic rays get into the soil. And we see that with the alluvial cell Lewis diamonds that we measured, that all of their isotopic compositions are actually lower than mid-oceanic rich basalts, which suggests that the amount of 3 helium formed by cosmogenic reactions is actually very low. And for the kimberlitic diamonds from Collier 4 and Jurina 5, the amount of cosmogenic 3 helium is much less likely to happen. So then when we look at our samples, the helium isotopic composition versus the carbon isotopic composition, we see two trends. One is around the -5 mantle value for carbon isotopes, and it has a range in helium isotopic compositions all the way up to the highest measured values to date for ocean island basalts, which is close to 50 R/Ra. So this likely is a mix between a high free helium-4 helium source and both morb-like sources and some crustal inputs for the values that are lower. Trend B, as you can see over here, with a lower carbon isotope value, the helium isotopic composition is actually going up as well. And this is likely, again, due to an influence of a higher free helium-4 helium source, and pelagic sediments likely have lower uranium thorium compared to oceanic lithosphere and crust, which is why a high free helium-4 helium source would have a bigger influence in the samples that have lower carbon isotopic values. So what's the evidence that it's actually a high free helium-4 helium source, not just the isotopic composition, but also because in the past, people have suggested that a primordial reservoir is undegassed, so it should have higher concentrations. We see this in our samples as well, both in the Collier 4 and the Juina 5 samples from array B, that with increasing free helium and increasing 4 helium concentrations, the helium isotopic composition is going up with some values that are actually higher than mid-ocean rich basalts. So this must mean that the high free helium-4 helium source has high helium concentrations. So one thing that people suggested is that these high free helium-4 helium source is sampled by plumes. So there is actually evidence for a plume in the area that the diamonds are from. So we've got the Trindade plume track, which happens about 120 million years ago, which is close to the kimberlite eruption age. So probably the additional heat from this plume actually is related to forming these kimberlite eruptions. Further, there are a lot of alkaline rocks in the area from the same age, and we can actually see a fossil mantle plume beneath Brazil, as you can see in the images below, where the seismic imaging actually still shows remnants of this plume going past there. And further, the young ages of the mineral inclusions in the Juina diamonds at 101 million years, less than 500 million years, and probably around 380 million years if we assume the eclogitic formation model. Again, show that the diamonds also formed relatively young and probably are related to a plume. So this led us to suggest that there is actually mixing between a high free helium-4 helium source, likely delivered by a plume, and the recycled material that's present in the transition zone. So we have a mix between the pelagic sediments or altered oceanic crust and the plume, where the plume has high R/Ra and also has high helium concentrations. And this results in a mix that's in between the oceanic lithosphere and the plume. So when we actually look at the ocean island basalts, we see that for neodymium and lead isotopic compositions in dark blue, we see the high free helium-4 helium samples. They actually overlap with what we see for the depleted mantle. So based on the morb samples, which are the colorless white squares. And also for the thorium, we actually see that the high free helium-4 helium samples from ocean island basalts are depleted in thorium contents. The ocean island basalts that originate from a peridotite source are about 20% higher in nickel contents compared to mid-ocean rich basalts. And again, these lavas have high free helium-4 helium. And these authors proposed that a less degassed but nickel-rich source formed by core-mantle interaction during the crystallization of a melt-rich layer or a basal magma ocean actually created this, and this source continues to be sampled by mantle plumes. So further evidence for what this high free helium, 4 helium source might look like. So we already saw that it's nickel rich and likely also titanium, tantalum, and niobium rich, and it's depleted in thorium, and neodymium and lead compositions are similar to mid-ocean rich basalts. And people have looked at ocean island basalts both for the helium and for the tungsten. And we see that the high 3 helium 4 helium ratios are associated with lower tungsten, so depleted in 182 tungsten. So some really interesting questions that we could still answer are by looking at the iron, nickel, carbon, and sulfur rich inclusions in super deep diamonds that have both mid-ocean rich basalt-like and low carbonized values, as you can see in the diagram below. And these lower mantle diamonds are, they have these metallic inclusions. And because the tungsten is often associated with like the metal, it would be really interesting to see if these fluid forming super deep diamonds are actually depleted in tungsten isotopes as well. And one of the other sources for this high 3 helium 4 helium source could be some of the mega ultra low velocity zones, which lie, for example, beneath Hawaii and Samoa and Iceland. So in conclusion, I hope I've shown enough evidence with the trace elements and the carbon, lead, and strontium isotopic compositions, and also the low 3 helium 4 helium for some of these diamonds, that we do see the recycled material signatures. We also see the high 3 helium 4 helium ratios with high helium concentrations, and in combination with the plume evidence in the area. And the depth constraints of these diamonds, that most of them are formed in the transition zone, this places constraints about the depth of the high 3 helium 4 helium source, which must be over 410 kilometers depth, but likely much lower. So we think the high 3 helium 4 helium source actually infiltrates the transition zone, for example, by this plume. And the range of compositions that we see in these diamonds actually show that the transition zone must be really complex. And these deep mixing between the plume and the recycled material can create a range of chemical compositions that we see in the diamonds, and we also see those in the ocean island basalts. So perhaps some of the ocean island basalt signatures are actually created in the transition zone. So thank you very much for your attention. And are there any questions?
Okay, thank you very much. Now it's time for questions from the audience. So for our participants, when you ask a question, please first let us introduce your name and your institution. So feel free to open your mic or type a question in the chatting block.
Can you hear me?
Yes.
Yeah, hi. Thank you, Dr. Timmerman. This is Hui-Min Bond from LSU. I have a very good talk, very comprehensive. I learned a lot. One question I have is that are you assuming all the carbon that forming the diamond has to be coming from the surface? It's not something that deep in the core mantle boundary or low mantle. It has to come from the surface. Is that the assumption? you have?
So we know from seismic imaging and also from sort of the signatures that we see in these super deep diamonds that there must be subduction of a slab into the transition zone. And obviously when we heat the subducted material in the transition zone, it's easy to actually create carbonate melts from the carbon that's already present in the subducting slab. So most of the carbon is probably coming from the recycled material, but obviously the altered oceanic crust can have compositions that are very similar to the mantle. And when the fluids interact with the ambient mantle just above the recycled material, that can also result in a creation of diamonds that actually have a mantle-like carbon isotope value. But yeah, probably most of the carbon is coming from the subducted material.
So the helium actually is obtained when this deep, let's say this is deep helium. It's actually come up through the from the deep and get into the transition zone, then mixed with this diamond there and get formed. It's not like something formed from very deep. Let's say the slow D zone, then brought up.
Yeah, it's, I think probably the plume or whatever rising material there is that's in the transition zone is carrying this high free helium-4 helium signature. And because in the transition zone, the recycled material, particularly the pelagic sediments, like all the recycled material would have been stripped of helium subduction, but particularly the pelagic sediments, because they're quite low in uranium and thorium as well, there is not a lot of 4 helium creation. So whatever high free helium-4 helium signature you're bringing in is going to majorly affect the noble gas, the helium composition of the diamonds, whereas the carbon is mostly coming from the recycled material. So you get sort of a mix. You see the helium is influenced by this plume or this rising material, whereas the carbon is mostly dominantly, it's dominated by the recycled material.
Okay, so and then the nitrogen aggregate and nitrogen in the diamond, because the quantity is so low, you pretty much won't be able to measure anything or like the isotopes to collaborate with your explanation. Can you?
Yeah, it's something we thought about, but because most of our diamonds actually have very low nitrogen, it's very difficult to measure the nitrogen isotope composition. Like below 70 ppm, you really won't be able to analyze.
You need a big diamond to do that, to cook it.
Well, it's easiest to do it by SIMS, because then you can do it, in the same spots we do for the carbon isotopes. Obviously, if we've got a big diamond, we could analyze it, by combustion. CERM's mass spectrometer, but then your diamond would be gone. Then you can't analyze your trace elements or your lead or helium. So it's a choice.
You probably don't expect any big change in the nitrogen isotope anyway. You probably expect it's organic matter. Then it's a 5 per mil, 4 per mil, something. It's not that different from, you don't know. It could be down there. It's mental source, it could be 5 per mil, you couldn't tell probably.
Yeah, so I don't know if you've seen Margot's talk last week. I think she had a diagram for nitrogen there. We actually see that the few diamonds that have been measured for nitrogen isotopes, for the super deep diamonds, the majority is very much mantle-like, and there are only a few that are having really negative nitrogen isotope values. Okay,
final question. So since nitrogen is very much like the mantle diamond, your data didn't really refute or negate the idea that the deep mantle carbon, the one that's not from surface, could actually have very native delta C13 value?
Yeah, I think it's hard to say that with my samples, because we also see the trace elements in the lead and the strontium that we really have that recycling component. So I'd be very hesitant to say that our very low carbon isotope values are from something else other than recycled material.
Good. Thank you.
Okay, next question, please.
Hello? Can you hear me?
Yes, I can.
Oh, yeah, I'm Xiaobin. I'm from Nanjing University. So I have two questions for you. One question is, so what's the typical size of your sample, the diamond?
So it varies. The smallest ones are about 2 to 3 millimeters in diameter, and the biggest ones are closer to about 7 millimeters.
So I'm wondering, so if there's some relationship between the size and the concentration and the isotope compositions.
Yeah, we've looked at this, like we plotted the helium isotopic compositions and the concentrations versus like the sample size. But we couldn't see any clear correlation there. So yeah, it doesn't seem that there is any, correlation to the size of the diamonds.
Okay, thank you. So another question is, so can you determine where the diamond exactly formed, the depths of the formation depths of the diamond?
Like this is something that's very hard to say, because most of our diamonds didn't have multiple mineral inclusions to really determine the exact depth. But we know from other studies from these locations that like 99.9% is super deep. So they're somewhere between 350 and 700 kilometers depth. But based on seismic imaging, we know that most of the recycled material is actually collecting and stagnating in the transition zone. So that's why we basically, talked about our samples being from the transition zone, or at least, providing that minimum depth constraint of 410 kilometers, because we see all these recycling signatures as well, in addition to knowing that they're super deep, even though we don't know an exact depth.
Okay, so I mean, is it possible, like the diamond like grows or contaminated by the subducted material at a different place? I mean, rather than the transition zone.
Because nothing goes in or out of the diamond after it's formed. Basically, all these fluid inclusions and micro minerals, they're protected. So it wouldn't have been able to be contaminated by recycled material afterwards, like after formation. Same for the carbon isotopes in the diamond, like that's locked in, like it doesn't diffuse in or out. So the signatures that we see, they're definitely not contamination. That's the recycling signatures are from the source, from where these diamonds came from.
Okay, thank you.
That reminds me of one of the questions I forgot to ask. You're talking about the helium diffusion extremely slow in diamond. So it pretty much retained the helium that during the time it's formation. What about the olivine mineral? I forgot how fast the diffusion rate is for helium in olivine crystal.
I don't know from the top of my head, but it's several orders of magnitude faster. So the main
Was that going to be a problem in terms of retain the signal?
well, it doesn't matter for the diamonds, like whatever is locked up,
Okay.
because there's diamonds around it. It
Mm.
doesn't go out. So it can diffuse.
But I don't have a diamond. I only have olivine.
I think that's one of the main reasons why we don't know so well. Like if we go back to, like that's one of the main reasons why we don't know so well what is happening with the helium isotope evolution through time, is because if we find xenoliths or ocean island basalts that are, you know, several tens to hundreds of million years old, or even billion years,
Yeah.
the gases are gone. Because, you know, once they're brought up to the surface, because if the diffusion,
Yes.
we're losing
Yeah.
it, conductionate. So yeah, I think it's very difficult to use older samples that we find at the Earth's surface to analyze, you know.
So you think that there are actually a lot of those fundamental parameters that need to be calibrated, not, you know, not just so helium in let's say in chert and feldspar and in olivine, their diffusion rate on the different temperature, pressure, mineral structure, all these are actually not very well calibrated yet.
Yeah, that's true. And like if we want to use those type of
Yeah.
you know, to use them for Nobel gas studies, we're going to need to know those diffusion rates to make corrections.
Yeah. I thought you know the Bruce Watson's group is actually interested in calibrating these parameters. It looks like most people in the community is actually interested in the flashy story rather than, you know, sit down and then doing these systematic calibration before go out and tell a big sexy story. That means the culture of our group. Who has a patience to sit down and calibrate these parameters?
Sort of papers, you know, once you get some good numbers that everybody can use, like
Yeah.
you know, use that.
Good.
The other main things that's still really not that well constrained is actually the partition coefficients of uranium, thorium, and helium between the minerals and the melts. So that's us that, you know, to make these models, we have to make assumptions about how much helium and how much uranium and thorium we're actually losing through melt depletions. So yeah, Harman 2007 and 2005 did some constraints, but it's still really tricky to say if we're losing more uranium thorium or more free helium. Like it's still like it flips back and forth between papers, which one is more incompatible. Extremely incompatible, but which one is more incompatible relative to the other is still very much up in the air.
I see, yeah.
I think this is something else we really need to work on, because that's going to be really useful for modeling as well, not just for real samples, but for
I agree.
those things.
So what are you doing now in Toronto? Is that right? As your postdoc? Yeah. What are you up to right now?
So after my PhD in Australia, I first had a short postdoc in Germany where I worked on sulfur isotopes of mid-oceanic rich basalts, and now I'm back to the diamonds.
Back to the diamonds. Okay.
Yeah, one of the things we don't know that well, there are only like 3 or 4 age constraints on super deep diamonds. That's not
true.
many minerals that we can date. So this is what I'm working on at the moment, to actually determine more ages of super deep diamonds.
Yes, it's a good thing, because at least you know the helium signal is reliable. It doesn't change, and then if you can get the timing, dates, the age determined, you can have a lot of story.
I know, and especially coupling it to the deep carbon cycle to get better age, you know, with the diamonds.
Cool.
So,
good. Thank you.
Yeah, I will continue the conversation in terms of the diffusion rate. Actually, I cast doubt on the assuming that the diamond is a forever capsule for all the elements. Like say different, like say for large cations, of course, it's hard for them to diffuse out the diamonds. But for hydrogen or helium, it's hard to say. For hydrogen, it's more likely from the evidences that I could list. Hydrogen is more likely could diffuse in and out of diamonds. For example, people do find the graphite inclusions. Some of them were used to possibly be methanes, and then the hydrogen diffuse out, left it behind. And there were also high pressure experiments that the diamond emerald cell people have been doing. I'm seeing that hydrogen diffusing out of the diamonds, that when they perform an experience, that they're trying to keep the fluids, but they could not, and at extremely high pressure conditions. So that's another sign that hydrogen potentially could diffuse out of diamonds.
One of the main problems with doing experiments is that obviously often like the grain size, like they're using either polycrystalline samples or
for those, a lot of experiments, like I say, it is the envelopes that when they do the experiments. So those, a lot of diamonds are single crystal diamonds. It has a very few defects. So it's
going to be very difficult to measure that because it's a gas. Like and to analyze helium, you know, you're going to have to.
Yeah. I know. Yeah, I know it's very hard. Like I said, so far there were no systematic work to prove that or to measure the diffusion rate. Maybe the diffusion rate is extremely slow. That to the scale, time scale, million year to billion year scale, it may diffuse only for 1 micron, for example. Then it doesn't matter for the case that when we explain the natural samples. But there is a possibility for that. Also, if we look at the crystal structure of diamonds, it is not entirely impossible for hydrogen or helium to go in through. I mean, when we talk about, let's say, the probably there.
I know there's
sorry.
I know there's a lot of debate around this. Looked at both fibrous samples and monocrystalline diamonds up to 2.3 billion years old, and I've heard like the different growth zones that I saw in the catalogues images. Like I've broken them into, you know, to the different fractions, and I see different isotopic compositions for some of those diamonds. Not for all of them. Some of them have, you know, similar compositions, but most of them actually show differences in concentrations and in isotopic compositions. Those would not exist if diffusion was a major problem. Like if the diffusion rate was high, we would erase any concentration differences and any isotopic compositional differences between growth zones.
Yeah, I don't claim that all natural samples that experience this process. Like I say, even for diffusion to occur, it could only occur under certain circumstances. I mean, even for hydrogen to if it diffuse in and out of diamonds, they have to satisfy different conditions because after all, there are defects in diamonds too, and also depends on how hydrogen couple with the different defects to diffuse, or the diffuse as a proton, but the two different stories. I think that leaves a lot of more work for people doing laboratory experiments as well as the first principle calculations.
Sure.
Actually, Jianhua, actually, when I had a conversation with Jianhua Wang from Carnegie, he measured a lot of diamonds that measured the hydrogen concentration. But in the end, he didn't measure anything by seams because of the all background noise. But I could understand that because for a lot of natural diamonds I get, either they are really, let's say, being like the hydrogen free, or the other possibility is that after all, for all the elements among the periodic table, that for the different elements diffuse into the earth material, so that hydrogen is normally always the fastest. So I think it's common that he could not see anything, but you cannot rule out that let's say occurs certain situation. But I don't know how big scale and what's the detailed mechanism. That leaves a lot of work for people to do.
Yeah, well, I think for the super deep diamonds in this case, it's not going to be an issue because we know from the few diamond ages that are there and from all the plume evidence that these diamonds likely formed only very shortly before kimberlite eruption. We're probably only talking a few million years rather than you know, the billions of years that we see for some of the lithospheric diamonds. So,
are there similar micro zoning study of the helium isotope composition on zircon? You know, here you have diamond. Do they have similar one for zircon or olivine? You know, different band, different rain, different overgrowth.
I would hope people have done this. I haven't looked into detail if people have looked at those things. Like even within the diamond world, some people are like, oh, you know, you can just measure them all together, and this is what people have done in the past. They just measure all diamonds. But we know from carbon isotopes that there are differences throughout the diamonds. So it doesn't make sense to measure whole diamonds for noble gases if you can see differences in growth structure and in carbon isotopes. Like I think you need to divide them up because you don't know if the helium is going to show a difference.
So about zircon, I was asking, what about zircon? Anyone see the same banding?
I don't know. I would have to look this up.
Okay.
Okay, any other questions from the audience? Okay, thank you very much for giving this talk, and thanks everybody for participating and involving in the interaction. Okay, have a good day, everybody.